particulate nature of matter. We have already studied kinetic theory of matter and solid, liquid and gases. So now we are going to extend our discussion and we are going to discuss the third topic, that is change of state of matter. Change of state of matter. You would have seen that we have studied what is matter, what it looks like and how it behaves, and we also gave some concept regarding under what set of conditions what a particular substance can be called as solid, liquid or gas. In kinetic theory of matter we have studied what are different postulates, what it explains. So in kinetic theory of matter already we have studied two major points, that is that in case of matter the particles continue to move, right? And the second thing we studied in the last video, that how the particles are arranged when we consider solid, liquid or gases. What is the arrangement they follow? Random, regular, right? So now today we are going to discuss how can we convert solid into liquid, liquid into gas and vice versa, or is there any unusual change of state where we can directly jump from one state to another without being converted into the intermediate state, right? So let's continue. So first of all, I'll make a small flow chart which will indicate how can we convert different states of matter into one another, right? So the flow of chart is like this: solid to liquid and liquid to gas. If we want to convert solid to liquid or liquid to gas or gas to liquid and liquid to solid, or we can directly go from solid to gas and gas to solid, right? So it means these are the change of states which are possible, where you can jump from one state to another and then another one in continuation, or maybe directly you can jump, as I have shown here, solid to gas or gas to solid without being converted into liquid state. Such states are called unusual change of state, right? So now what do we call these particular processes? Now see, so if we want to convert solid into liquid, we call this process melting. If I want to convert liquid into solid, we call it freezing. If I want to convert liquid into gas, we all know it is evaporation. And if we want to convert gas into liquid, condensation. Right? So if I want to convert solid to liquid, it's melting, or if I want to convert liquid to solid, or if these big arrows are confusing you, we can turn them into short like this. You can also say liquid to solid or solid to liquid. So I can also show it like this. This is freezing. Similarly here, if this big arrow is creating any kind of confusion, we can also show it like that. It's up to us how we want to present it. So it will be your condensation. Right? So in that case, we don't have to show this. So you can make it again. I am making changes in the same diagram. Next is, if we want to convert used, that is called sublimation. And if I want to convert gas into solid, there's a word called deposition. Right? So these are the names of processes. Sometime in just MCQs maybe, or in structure paper in just 1 or 2 mark definition, they may ask what is this change of state being called as, right? Usually if they want to ask question in IGCSE, in this section, you may get questions from multiple choice. There are less chances to ask questions from like structure and alternative to practical, right? So in this case, solid to liquid is melting, liquid to solid is freezing, liquid to gas is evaporation. As I have told you already, you can also make it like that, up to you how you want to present it. So I have made both the changes in the same flow chart or same kind of diagram. So gas to liquid is condensation, and gas to solid is deposition, and solid to gas is sublimation. Now it won't happen just like that as we are writing so easily in case of this diagram. So there are certain set of conditions, right? So what are those set of conditions where we can change one state to another? So now I'm going to explain the simpler ones where you can convert solid to liquid and liquid to gas. The same concept you can apply to change any state, right? The matter is we have to understand what is the factor, what are the parameters which are playing a role when we want to change one state to another. So now one by one we will understand, first of all, solid to liquid transition, that what we have to change, what we have to take care of, and if we are making some change or if we are providing some condition, how that condition is fulfilling the requirement to convert one state to another. Like a simplest example that we all know, ice to water, water to steam, right? This is a very simple thing, everybody knows. Even if you don't know science, you know that if you keep ice at room temperature, it will turn into liquid. If you want to keep liquid at room temperature, even if you are not heating it up, it will evaporate. Few examples. Now you will say, how is it possible? We all know it is possible. Okay, suppose in hot weather, suppose you sprinkle some water on the flowers, or maybe on the roof, maybe in your balcony, to just make it quite chill. After some time, if you go after 1 hour, there will be no water. It's evaporated. It has been turned into gas, right? Suppose now clothes are wet. If you want to dry them in the sun, if you go after 4 or 5 hours, what will you see? Will they still be wet? It means the water present in the clothes was drained and converted into vapors and went into the sky. So it means even if we are not providing heat, liquid is changing into gas, but not for every substance, right? So let's continue the discussion and go into the core detail how solid can be converted into liquid at microscopic level. We need to know some information because when we write in exam, we need to know some key points. So always when I explain, I always highlight the key points which are extremely required when you write the answer. Otherwise, if your explanation is valid but your key points are missing, in every lesson I will give you guidelines, you will not get the credit for your answer because nobody is going to study the explanation. You have to use specific scientific keywords which will conduct the whole meaning, that don't have to write the explanation. And in IGCSE, as there is a working paper, there is finite space, so you have to write your answer in that space provided. You cannot extend it, otherwise again it will not be considered, right? So let's study further. Okay, so suppose we start from solid. Okay, in solids the particles, as I have already told in the previous video, the particles are very, very close. Okay, this thing we all know very well. If you want to convert solid into liquid, you need to give heat energy. If you will not give, I'm not saying you to take ice and just put it over the flame and then you heat it. If you will not give heat, see, in every process it's not required that we have to give heat. Sometimes what it will do is it will take heat from the surroundings. If the surrounding temperature, because we know ice is cold, the surrounding temperature is higher than ice, right? So it means it will absorb heat from the surroundings. But it's not in case of every substance. I'm taking a simple example so that you can understand it nicely. So suppose let's take the example of ice, because we know ice temperature is colder as compared to the surrounding temperature. So it will take or start receiving heat from the surroundings. Okay, so heat is coming, you are not giving. Yeah, definitely if you will give and you will put it over the flame and you will light up a burner below it, it will be faster of course. But it can happen even at room temperature. But mind it, not for every substance. If I want to melt iron, I cannot do it at room temperature. I need to give a specific heat energy. Okay. So solids, the particles are very, very close. So now what we are doing is, now we are going to understand the third scientific aspect for kinetic theory of matter, right? First aspect was that the particles are moving in matter. Second aspect was there is a specific arrangement. And the third aspect was change of state of matter. So now understand it. So if we give heat energy, then what will happen? as particles will get energy, they will start vibrating faster. As we have discussed already, that even in solids, the particles are vibrating at their main positions, right? So when they vibrate, if you give them energy, they start vibrating faster, 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 right? So when they start vibrating faster, what they do is, suppose I'm standing here, right? And there are two people holding my hand. So one surrounding my left, one surrounding my right. Similarly, to these people, other people are standing on right and left and surrounding them. Suppose we are doing some dance and I'm slowly moving on the left, slowly moving on the right, it's fine. Suppose someone says to dance very fast, 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 fast. Then what will happen? If there is a finite space, the space is still, but we have to move faster. In that case, I will hit my surrounding person on the left or maybe on right faster with more energy. Then maybe I'll push him a bit away. Similarly on the right, I'll push him a bit away. So same happens in case of solids. Solid, there is a definite shape. Particles are locked in that definite shape. So if you give them energy, they start vibrating faster. And when they start vibrating faster, in that case, they push the neighboring molecule, right? So if solid gets heated, vibration becomes faster. Vibration of particles gets faster. Next, right? When vibration gets faster, the particles will start pushing their neighbor or adjacent molecules, right? So results in pushing of neighboring particles faster. Okay, when it happens, then suppose particles are now pushing each other faster, so they are slightly going away from each other, or depending upon how much heat energy you are giving and on the substance, nature of substance as well. So if particles start moving away, suppose I'm a particle, the particle next to me is going slightly away, particle right on me slightly going away, similarly the particle next to him will go away. So particles if slightly going away from each other, say this particle is going away, then this is also going away, this is also going away, then volume of solid increases. Volume of solid increases. If volume of solid increases, it means your solid is expanding. Okay, it means particles are pushing off each other, their volume is increased. It means we call this stage as expansion of solids. So solid is expanding. So this is one part where we can see that if we give heat energy, then what will happen, right? Now the second part is, this is the part that we have said that we have explained the consequence of heat energy in terms of vibration of particles. Now the next phase is, what will happen on the arrangement, right? Will the arrangement gets disturbed? Because we know solid has a regular arrangement. So if we give heat energy, how can we disturb that regular arrangement? Because if particles have a regular arrangement, they cannot be turned into liquid. Okay, so just note it down quickly, and then we will move that how it affects when we give heat energy, then how it affects your arrangement. Okay, so let's move further and continue our discussion. Okay, so now we know that if we speak about solid, there is a force of attraction between the particles. That's why they are closer. This we have already discussed in detail in the last topic in the last video, okay, that solids have the stronger force of attraction, right? So if solids have a stronger force of attraction, if you want to convert them into liquid have less force of attraction. So first of all, that force of attraction breaks. If force of attraction breaks, then only you can move them away. If that force of attraction breaks and the particles start moving away, it means the regular arrangement will also be disturbed. Okay, so let me write it. So if we give heat energy to solids, then the force of attraction between the particles becomes weaker. If force of attraction becomes weaker, it means the regular arrangement in case of solids will start to collapse or break down. The regular arrangement starts breaking. Okay. It means if regular arrangement will start breaking, then what we can say? It means the particles will start moving away from each other, right? It means what we have done is, what is the difference between solid and liquid? We have studied already in detail. In solid, the particles are closer. They are closer, they have strong force of attraction, they are in a regular arrangement. But when you give heat energy, what will happen? Vibration becomes faster, due to which they start pushing off their adjacent molecules. When they start pushing their adjacent molecules, then what will happen? The force of attraction between them weakens, and as it weakens, then ultimately we know that the regular arrangement, this regular arrangement will start breaking and particles start moving away from each other. And as it happens, particles start moving away from each other. Then what's next? Melting. It means solid starts to melt. It's not completely melted. It just starts to melt. So this is that state where we say now solid has started melting. So solid will start to melt. And the temperature at which you can make temperature is known as melting point. So melting point is the temperature at which solid can be converted into liquid state. So what is melting point? The temperature at which solid can be converted to liquid state. So now we have reached to melting point, but this is not an easy step as we say, okay, ice is melting if we keep it at room temperature. There are a lot of things which are happening at the molecular level. Vibration or a breaking of regular arrangement, weakening of the force of attraction, and then movement of particles. Then solid is converting into liquid. So please have a note of it, then we will begin further. Okay, so now let's continue further. Now few things, if we speak about melting point, there are few things we have to understand, because after this topic we will study curves, heating and cooling curves. So I'll explain you heating curve, the cooling curve is just the opposite, right? So now if we speak about melting points, you may get question based on this. In experimental, your practical or alternative to practical paper. If we speak about melting point, sometime in just one liner they ask, how can you determine the melting point of a substance, right? What is the method you will use? Okay. Second question that they can ask is, how can you say that a particular solid is pure? Okay, so you have, suppose you have done some experiment where you are getting crystals, and how will you check the purity of crystals? This will be the question. How will you check the purity of the crystal? If the crystals are having a sharp melting point, always in such type of questions, always see, are they asking for solid? Students always do this mistake. They always write sharp melting point, boiling point. No. See, are they asking for solid or they are asking for liquid? If they are asking for a solid, what you have to say is, if it is a pure solid, it will have a sharp melting point. If it is impure, sometime in tabular form, they will give you a range, right? Say 45 to 50, 43 to 42, and they will ask in the table, in this information, which one you consider as impure sample. So where you find that there is a range given, it means that sample is impure. So if a sharp melting point is given, always see, are they asking for solid or liquid? Never write sharp melting or boiling points. It will be an invalid answer. Okay. So when we are asking for melting point, it means sharp melting point, pure solid. Okay. And range, impure solid. Now, if the solid is pure, if it is impure, definitely it will show a range. But if your solid is pure and you know that it is pure, in that case the temperature of the mixture or the reaction mixture, suppose you are melting a solid, the temperature will not rise till whole of the solid has been converted into liquid. If full solid is being converted into liquid, there is no solid particle left behind, then only you will see the temperature will start rising further. So temperature will remain constant until whole of the solid gets melted. So this you have to make a note. The temperature or melting point will remain constant until whole of the solid substance has been melted, right? So this is second important point. Third, now high melting point and low melting point. This is also very, very important for questions point of view, because you know in your international boards you will not get direct question what is melting point. They will give you some examples, they will give you some applications, based on that they will revolve the question around it. Okay, so if somebody is asking, suppose 10 compounds are given to you, suppose a table is given to you, in that table they are giving you some melting points details, right? So what you have to get the inference about from the table. So if they are asking which one of the following is having high melting point, or suppose melting points are given, how will you categorize the molecules, right? Always consider, if you have metals, they have high melting point, or if you have ionic compounds, they have high melting points. Non-metals, they have low melting points. Most of the non-metals, except your graphite and diamond, most of the non-metals, they have very low melting points, because most of them are existing as liquids or as gases, right? So substances having high melting point, example metals and ionic compounds. So this is in general, and I have told you graphite and diamond, that is the exception for non-metals. Otherwise non-metals, they have low melting and boiling points, right? And the next conclusion, if we have high melting point, it means there is a stronger force of attraction. Suppose some example is given to you. Why diamond is having high melting point? What will you write? Suppose somebody is giving you some example like ionic compound NaCl. Why sodium chloride is having high melting point? Suppose the question is in 2 marks. How will you explain it? So, first of all, always remember that 2 marks means you have to write 2 different points. It's not like 1 point just explaining in detail. It will be considered as 1 point. 2 points like, if the melting point is high, it means there is stronger force of attraction. Point number 1. Point number 2 is, you need large amount of heat of energy, right, to break that arrangement. So one is stronger force of attraction. Second, it requires higher amount of energy. It means the melting point will be high. So this information was for your solids, and please make a note, and then we will continue for liquids. Okay, so now let's start for liquids. Okay, so if this is the liquid, let's see, already we have seen happen for liquids. Now I will tell you what is different in liquids, right? Because definitely solids, there is regular arrangement, strongest force of attraction. Liquid, it's slightly different. So let's see how it will be different in case of liquids. Now see, liquids, as particles have space between them. So if you give heat energy, the particles will move even faster because they have space. Suppose you want to walk fast, right? Suppose you want to walk fast, but there is a person standing very close to you, here. One person is here, one person is here, one person at the back. If you want to walk really fast, can you walk? No. As in case of solids, close packed, a regular arrangement, surrounding by molecules immediately on the left, right, back, forth. So it means you cannot walk faster. Suppose there is a space. You are standing here, the next person is standing 4 feet away, and you all are walking together. Suppose you are walking, the other person is also walking, so there is more probability to get faster. Okay, so here the particles will move even faster. So the first point is, as now we are continuing for liquids, particles will move even faster. Why? Now the question, next question that should click us is why. As I have explained you, this is a normal one that I have explained you. In normal life also we see, if there is, suppose I'm walking on the road on my foot, or I'm driving a car, if there is no crowd, there is space between the cars, I can drive fast. If it is heavily congested, then I have to control my speed. Okay, so now what is the reason behind it? If I say particles will move even faster, because if you give heat energy, that heat energy will be distributed to all the particles, right? So that's why in solid, suppose you are heating one corner, maybe it's not equally distributed to all the particles. Suppose this is a big block, suppose you are heating only one part, it will take time, right? Liquid, because particles are continuously moving, they will transfer their energy, they will collide with each other. So the energy, so what we use a particular word that called average energy. As I have told you, if particles are moving, the energy used is kinetic energy, right? So when we say that particles are having kinetic energy, when you are giving energy overall, because every particle is walking with a different velocity, moving with a different velocity. We cannot say that one particle is moving slowly, maybe other is moving faster. But we calculate average energy, total energy divided by number of molecules. So average kinetic energy increases, because average kinetic energy increases. So particles will move even faster because average kinetic energy increases, right? Now next, see, Now these are the particles, right? These particles are present in the bulk, and these particles are present at the surface. If you give heat energy to liquid, the particles which are present in the bulk, they take energy and travel to the surface. And the particles which are present at the surface, if you give them energy, they will leave the surface and change into vapors. So the particles which are present here, already present here, they will leave the surface, take energy and go into the vapor phase. And the particles which are present in the bulk, they will take energy and go to the surface. So two things are happening. If particle are present here, they are getting energy, heat energy, and they are moving up to the surface. And the particle which are at the surface, if they take energy, they move into the vapor phase. And if particles move into vapor phase, we call it evaporation. It means liquid is converting into gas here, right? So if we give heat energy, particles from the surface of liquid will take the energy and move into the vapor phase. Okay, so this is happening when you are giving, and now we know that evaporation can happen even at room temperature, but that temperature is not known as boiling point. So what is boiling point? If you are continue to give heat energy, this movement, bulk to surface, this movement becomes faster. If it becomes faster, then what happens? Suppose they are going very fast from bulk to surface. So you can see that bubbles will start forming into the liquid, right? If bubbles will start to form into the liquid, that temperature is called boiling point. Okay, so bubbles will start forming in the bulk of liquid This temperature is known as boiling point. Okay, so now I have explained you two things. That evaporation means you are giving heat energy. Even if you will not give, they will take from the environment if it is not so cold, right? Because we know in cold weather, suppose I spill water in the garden or maybe on the roof, maybe in my room, it will take time to get it evaporated because it's so cold even outside. But if weather is hot, 1-2 hours, it will automatically dry up. Okay, so it means then this will happen. Then particle from bulk will go to surface. From surface, they take energy and convert into vapors. But if the process becomes rapid, suppose you keep the water over the flame, then what will happen? After putting over the flame, then particles will get energy very, very fast. They will start moving very, very fast from bulk to the surface. You will see bubbles will form. That is the indication boiling point is reached. Again, boiling point will not rise further, or the temperature will not rise further till whole of the liquid that you have taken is converted into vapors. Once whole of the liquid is converted into vapors, then there is only gas. Then you can increase or decrease temperature. Till then the boiling point is there, that is constant. You cannot increase the boiling point above 100 in case of water. So this is the case of liquids. Please have a note, then we will continue further. Okay, so now next, Okay, so as we have seen in case of liquids and solids, in solids what did we see? In case of solids we have seen that if there is high melting point, it means same 3 points will be right here. If there is high melting point, it means there is a stronger force of attraction. If there is a low melting point, there is less force of attraction. Similarly, in case of liquids, if there is high boiling point, it means stronger force of attraction. So if I say high boiling point, stronger force of attraction. Boiling point will not rise further. One second, I have missed out point, sorry. Boiling point will not rise further till whole of the liquid has melted, has boiled off, or converted into vapors. Okay, so boiling point will not rise further. One more thing that we discussed in case of solids. What is that? Just one second more. So if we think sharp boiling point, it is a pure liquid. If it is a range, it means it is impure. So sharp melting point, solid, pure solid. Sharp boiling point, a pure liquid. So this is the case for liquid. Let's solve for the liquid, have a note, and then we will move further. Right, so let's go for gases. So we have already seen solid to liquid, change of state, liquid to gas, now gas to liquid. So reverse. So we have seen already, if you want to convert solid to liquid, you need to give heat energy. It means you need to increase the temperature of the solid, then it can convert into liquid. Similarly, if we want to convert liquid into gas, again we need to give heat energy and you need to increase the temperature of the liquid. So in conclusion, what can I say that? If I want to convert solid to liquid, temperature should increase. Liquid to gas, temperature should increase. This is my increase symbol, up arrow, right? If I want to come back, suppose I want to convert liquid to solid, what do we do? Let's take a very simple example, water that everybody knows. If I want to convert my water, liquid water into ice, I have to keep it in the refrigerator. It means I am decreasing temperature. So liquid to solid is decreasing temperature. This is down arrow, it always show decrease for me. Okay, so now if I want to convert gas into liquid, what I have to do is decrease temperature. So decrease temperature. Then what will happen? When we heated up liquid, we understood that average energy, average kinetic energy of all particles will increase. Maybe one particle is having low or a high, but we take average. The total energy divided by number of molecules. So average energy of particles will drop. Then cycle will reverse. If we were giving energy, then what was happening? Particles vibrating faster in solids. In liquids, the force of attraction was weakening. Then if force of attraction will weakens, then the particles will start coming close. In the previous case, we saw particles were moving away from each other. So if average kinetic energy of the particles drop, then, so should I rub this? This is a simple one that already we have discussed in detail. So I'm rubbing this one. So So the average kinetic energy of particles drop, right? If it is dropped, then force of attraction when we were heating, force of attraction was decreasing. When we are cooling, then force of attraction will increase. If force of attraction will increase, then particle will start coming close to each other. In liquids, when we were heating, the particles were moving away. So here the particles will come close to each other. And what do we call it? Condensation. It means now gas will liquefy, and the temperature at which will happen, it means it is condensation. Reverse process, right? So gas will liquefy. So temperature is not so important. Usually we take the other side, like solid is converting to liquid, melting point, liquid is converting to gas. That is your boiling point. The reverse sides, we don't take the temperatures, right? So the side, like left to right, is important. We should know what is melting point and boiling point, and I will explain you just after this what is the difference between evaporation and boiling. So gases will liquefy. This process is known as condensation. This process is known as condensation. So with this, solid, liquid, gas transitions, they are changing from one state to another in different conditions. In this case, we have to decrease temperature, then gas will convert into liquid. So this is done. Now just add to your knowledge one GK point, how evaporation and boiling point is different. Because we are saying evaporation can happen at any temperature, but there is a specific boiling point that is fixed for a particular liquid. Suppose we say water has 100, then there is no other liquid in this world which have the same boiling point. Why? Let's see. Now, difference between, we don't have to go in much detail, just a GK, add to your knowledge. If you want to write, it's fine, otherwise it's okay. Just keep in your mind that these two things are different. Evaporation, any temperature. Boiling point, fixed. So difference between evaporation and boiling point. Right? Evaporation means just change of state, liquid to gas. But boiling point, now see. Okay, as liquid will turn into vapors, we know that vapors or any gas, it always exerts a pressure. Gases always exert pressure. Even if you are cooking something in a pressure cooker, you are filling gas in balloon, it will always exert a pressure. If you fill it in excess, it will blast. Okay, so here the pressure which is exerted by these vapors, it's called vapor pressure. Right? So these vapors are exerting some pressure. But in air, there is atmospheric pressure. There are a lot of gases in air, right? These gases will also exert a pressure over everything on us, any experiment if we are performing, anything if we are doing. So that pressure is called atmospheric pressure, right? So the temperature at which vapor pressure of a liquid becomes equal to atmospheric pressure, this temperature is known as boiling point. So if this vapor pressure becomes equal to atmospheric pressure, that temperature is boiling point. So the more details will be in your higher classes, your IB, CB, ISC, whatever is. Okay, so this is the core, that vapor pressure. This is because of evaporation, and when it becomes equal to your air pressure, the atmospheric pressure outside, that is called boiling point. The temperature is known as boiling point, right? So now next, so now there are two unusual changes of state. One is called liquid crystal display. This is again GK. Maybe the question can be asked in your multiple choice paper. In structure and in ATP or in practical paper, you will not get question from liquid crystals. You can get more and more into your MCQ. So liquid crystals. Now, this is very interesting. Okay, we know LCDs, yeah, our laptops, our phones, watches, televisions, they have LCDs nowadays, trend of LCDs, right? That's called liquid crystal display. Now see, if we are saying liquid, it means it should have a property of liquid. The major property of liquid is they can flow. Crystals. Crystals means we are saying about solids. It means solid means the most remarkable property is there is an ordered arrangement of all the particles. So liquid crystals are the substances which can flow like a liquid but have order of particles like solid, like LCD. So these are liquid crystals. So the characteristics are they can flow like liquid, and they have order of particles as in solid. Examples, we know we have computer screens, we have your watches, digital watches, we have cell phones, and we have televisions, etc. So that's all example of liquid crystal. It is the unusual change of state. Have a note, then we will move further. Okay, next. There is one unusual state, that is direct conversion of solid to gas without being converted into liquid. So now solid to gas, and the process is called sublimation. Okay, so very beautiful example, when we do prayers, we use incense cones, we use incense sticks, we use camphor. If we burn them or if we lighten them up, it directly start producing fumes, the fragrance, the fumes. It means solid is directly converting into liquid. And we have iodine. If you do some experiment, maybe in most of the cases students do experiment in the lab. If you take iodine, what you do is a small experiment. I will tell you how to do it. If you have done in labs, it's well and good, but if you have not done, you can try it in your lab. So it is very interesting. Suppose you have taken iodine. This is your tripod stand. This is your burner. Use a funnel. Place it inverted over the evaporating dish. Plug some cotton here to prevent the escape of gas. Though it's not a very ideal experiment, gases will still leak from the sides, but still we can use it. Or then use paraffin wicks to seal it. Okay, so you take some iodine solid here, cover it with a inverted funnel and just heat it. If you heat it, you can see your solid iodine will convert into iodine vapors. After some time, you just keep the burner aside, turn it off, right? Cool it down. You can see that the crystals of solid, if you take the inverted funnel out, you can see that the sides will be having deposition of solid iodine. As we have seen in the flow chart, gas to solid is deposition. If you scrap it with spatula or something, you can see solid crystals of iodine will deposit over the walls of funnel, right? So this is experiment. We can directly convert solid into gas, right? One more thing is dry ice, like solid carbon dioxide. So in case of solid carbon dioxide, what happens if we cool down carbon dioxide gas to minus 78 degrees Celsius, it will convert into solid. It looks like ice. That's why we call it dry ice. So solid carbon dioxide is formed if we cool CO2 gas to minus 78 degrees C. It will turn into solid, right? So it is formed carbon dioxide gas to minus 78. It looks like ice, so we call it dry ice. So what happens when we convert solid into gas? Again, we have to give heat. Temperature will increase, regular arrangement will break, force of attraction will weaken, particles vibrate very, very faster, and finally what we get is the spreading of energy, because now solid to gas is a huge transition because you are mixing up liquid. So energy will spread faster to all the particles. That's why this change is very fast. Immediately solid to gas, right? So with this we have completed all the three major changes of state: solid to liquid, liquid to gas, and gas to liquid, and all other are unusual that can be done, but there is no specific like temperature for it. Okay, now there is one more important thing in this topic which is very, very important. You can get question from that topic in your structure paper, that is heating or cooling curve. So let's have a note of it. Okay, so now heating or so I'm making a heating curve. If you want, you can make cooling curve. It is also like this. Okay, so that is all. So let me explain it and let me label it. So now see, I am taking a range temperature. Temperature I am taking, temperature is increasing if we are going, because we have to label x and y axis. So this is the y axis, and temperature is increasing as we are going from bottom to top, and we are taking temperature in degrees Celsius. And here we are taking time, and time we are taking in minutes. Time is increasing from left to right. Okay, so this is the lowest temperature that we have taken, minus 15 degree, and we are making this heating curve for water. The transition that you will see here is ice to water and water to steam. Okay, so let's understand it. This is very, very important. See what will happen. Now you know all the details what will happen. So depending upon the mass distribution, we have to give all the details like force of attraction, regular arrangement, particles moving away, average kinetic energy. So all that we can explain now depends upon the marks. Suppose the question is in 4 marks, so write 4 different points regarding force of attraction, energy, vibration, particles, and if it is coming in 3, and up to you. Okay, so now see here. If I start with minus 15 degree, I know at this temperature the water will be in the form of ice, right? If I start increasing temperature, I know that till 0 degree it will still remain as ice, right? So it means 0 is the freezing point. So if I start increasing temperature above 0, 0 is also the melting point. right? Then solid will slowly start converting into liquid. So this is the first point when solid will start melting. So I say that this temperature is your melting point, right? So now see, in this area from here to here, temperature is constant. It is 0. What does it indicate? First of all, it indicates that it is a pure solid. That's why there is no fluctuation. Second thing, it indicates that, I have told you when we were discussing solid to liquid, when you are converting solid to liquid, then what will happen? The temperature will not rise further till whole of the solid has been melted. So it means here to here, solid is converting into liquid. So solid particles slowly converting into liquid. Till this point, solid liquid conversion is in process, but temperature will remain constant. So this is the point where the solid is completely converted into liquid. So if I say point A, and this is your point B. So point A, only solid, this is the melting point. Point B, when solid is completely converted into liquid. A to B means solid is converting into liquid. Here it is completely converted, at B we have only liquid. So now if you increase temperature, the temperature will increase. It will exponentially increase till 100 degree, right? So at this point there is only liquid. If we go from here to here, it's only solid. So here to here, it's only liquid, right? Now this point is known as boiling point. So this is the boiling point. So here liquid will convert into gas. So temperature is constant. So liquid is converting into gas, but temperature is constant. There is no rise or fall of temperature. It means the temperature will not rise for converting into, or has been converted into gas. So now see, here liquid is converting slowly into gas. This is the point where liquid will first start converting into gas. The first gas molecule is formed at C. So it will continue to happen till liquid is completely converted into gas. So this is the point D, where liquid is fully converted into gas, and this is the constant temperature. Here only the change of state is happening. Now you will think, okay, if I am giving heat continuously, where will the heat go if temperature is not rising? So that heat is just converting your liquid to gas. It means that that heat is used up to move the particles from bulk of the liquid to the surface, and from surface it is going to vapors. For that transition the heat is being used up. It is not resulting in rise of temperature. So till here liquid is converting into gas, and after this if you increase the temperature, because now temperature will increase but it is only gas, and after that it will level off. There will be no change, only gas particles. So this is the heating curve. So if the state is being changed, temperature is constant. Once one state is fully converted into other state, it means now the temperature will increase, right? That's why in these zones the temperature is constant but state is being converted. If the state is same, then temperature is rising. That is following the melting or boiling point of solid or liquid. Right? So in this video we have studied that how can we convert solid into liquid, liquid into gas, solid into gas, and vice versa, the reverse process. We have studied liquid crystals. We have studied if we give heat energy to any of the state of matter, how it disturbs the arrangement at molecular level, and what is the heating curve. If we go for cooling curve, it is just the opposite. So this part is really important for your structure paper. So see you soon in the next video with the next topic of particulate nature of matter. Till then, have a wonderful day, have a wonderful time. See you soon.